Hello, and welcome to Functional PHP 7 by Pact Publishing. My name is Luis Atencio. I'm a cloud engineer at Citrix Systems with over 10 years of experience architecting web apps using PHP, JavaScript, and Java. I'm also the author of Functional Programming in JavaScript, which covers a lot of the concepts we're going to be discussing in this course, except tailored to the JavaScript community, RxJS in Action, which combines functional and reactive paradigms, an open book called Functional PHP available at LeanPub, which discusses a lot of the topics we'll be looking at in this course, several magazine articles for phparc.com. I've spoken at several conferences involving both PHP or JavaScript, and you can follow my writing at luisatencio.net. This course teaches you how to think functionally, and this involves understanding a set of principles and techniques that will help you wrap your head around functional programming in general. Some of these techniques can be very powerful as well for regular day-to-day development. Things like understanding the use of higher order functions and the closure data type, the benefits of pure functions and what that does to the testability of your application, understanding the differences between lazy and eager evaluation, the advantages of using recursion over loops, a very powerful technique called curry function application that also leads into functional composition. We're going to learn how to convert programs that use large monolithic functions that perform data I/O, have several if-then-else conditions or for each. In other words, they have a high level of complexity. They're done imperatively, to a set of more fine-grained, smaller testable components that give you a declarative style of coding and are very much piped in the same way as Unix programs are put together. You could not have picked a better time to learn functional programming. Not only is it top of mind in the programming community, but it's also gotten very wide industry adoption by some companies that you might recognize. Also, platform manufacturers have understood the versatility that functional programming brings into the language, and so you see the emergence of functional features in Scala, in JavaScript, and Java with a recent Java 8 update, Python, and many other languages that can't mainstream languages that can be used functionally. Or you might just be looking for an alternative to OOP to solve some types of problems. Or maybe your motive is to just to enhance your programming and problem solving skills. Whatever it is, it's important to understand that PHP 7 is also a platform where you can learn to implement all of these techniques as well. The functional PHP 7 course is very lightweight in terms of installation and setup. The most important requirement for this course is that you have PHP 7.1 installed on any operating system of your choice. It could be Mac, Windows, or Linux. A lightweight IDE would be a good idea, like Sublime or Atom, but you could always use PHP Storm if that's what you prefer. Also, Composer for dependency management, as we're going to be incorporating some of the functional libraries in the ecosystem. And most importantly, the desire to learn something new, as we're going to be approaching concepts from a completely new perspective. I wanted to quickly show you the composer.json file that we're going to be managing throughout the course. We're going to be using the plambda library and the database library. This simple setup can be all provisioned through a simple composer install or composer update call. In our next video, we'll take a brief PHP 7 crash course. And there are two important topics that I would like to emphasize. The first one is PHP 7's static type mechanism. And that gives us the ability to create programs that are correct, and it gives us code correctness. And the second one is PHP's internal closure data type, and this is the root and the foundation for higher order functions. So let's begin this journey together, and I hope to see you there. Hello and welcome to Functional PHP 7. I'm very happy that you decided to tag along after all. So before we dive deeply into functional programming concepts, it's important to learn about some of the new features available in PHP 7, specifically the notion of static versus dynamic typing in a language. We're also going to be learning about the closure class and how this leads to something called lambda expressions, which are not available in PHP yet, but will become available in some time in the future. And then how we can use higher order functions to create more composable and succinct code. Without further ado, let's jump into our first video titled Static versus Dynamic Typing. In this video, we're going to take a look at the differences between static and dynamically typed code. We'll also take a look at PHP 7's new strict type declaration, as well as some examples of functions that use strict scalar types and return types. Now, the difference between static and dynamic are not very clear sometimes, and people gravitate religiously towards one or the other depending on the support that they're looking for in terms of compiler and things like that. But in a statically typed language, the type of a variable is always known at compile time, versus in a dynamic language where the type of the variable is really given to it at runtime depending on the conditions and how it's running. Code correctness is ensured by the compiler in statically typed languages, and this is something that's really powerful because this means that compiler is always making sure that the information you're passing into functions obeys and follows the type restrictions. Most often what happens in a dynamic language is that any typing issues we always find out at runtime. Statically typed code tends to be more verbose, and this is as a result of the same idea of adding type information to every single variable. And dynamically typed code is a lot more succinct, and so it's really used a lot for scripting and things like that. And in a statically typed language, you need to explicitly declare variables with their types before using it. And sometimes, as you know, in PHP, we can do tricks where we can dynamically instantiate or dynamically declare variables whether we need them or not. So conditionally in that case. Some examples of statically typed languages are languages like Java, C, C++, C#. Dynamic languages include PHP, any version of PHP before PHP 7, even though PHP 7 is also considered dynamically typed, also Python and JavaScript. And the reason I say before 7 is because we're introducing this notion of a language that is gradually typed. In other words, you can begin to turn on type checks by using this statement at the top of your file called declare strict types equals 1. And we're going to see that when we add type information into our code, it's going to become more correct and self-documented. And this is going to become very important later on when we talk about function composition, because the compiler will be able to give us information and guarantee that the order and the information passed into our functions is correct. And this also helps static code analysis tools and IDEs to make sure that it can figure out, using type inference, it can give you information about the methods and any of the member variables of a class, just because it knows ahead of time what type it is. And I'm also leaving you with some of the RFCs that led to these proposals. And here's an example of a strictly typed function. And as you'll see, when you want to turn on strict types, the first line in your PHP file would be the declaration to turn strict types equals 1. The function toCSV takes any string and looks out for the comma separator. And on that delimiter, it goes ahead and tokenizes it and expands it into an array. So the thing to notice here is the use of the strict scalar type into this, for the CSV variable, and the use of the scalar type return type. And what's going to happen here is that the PHP runtime engine will actually verify that the input and the output matches the function body. So instead of trying to coerce and turn the input type to a string so that it can use it in the explode function, it actually guarantees it actually looks for that type. So you must pass a string, otherwise you'll get an exception. And the same thing goes for the return type. First, include your declare statement. That way you can tell the PHP runtime to be checking for strict typing in your code. And so just to show this, we'll develop a quick simple function called add. And add is going to work over floating point numbers. So we'll take arguments a and b, and then obviously the return type that we want from this function of adding two floats is itself a float. And just like definition of add, that just returns the sum of variables a and b. We'll say this is addition of a and b, and then we'll pass two floating point numbers such as 2.5 and 2.5, so that we expect the output of that to be 5 as a float. So let's see if we can run that. And as you can see, the result is what we expected, 5. So let's go ahead and play with this a bit and change the second argument to be a string. So normal PHP would probably try to do some type of coercion, but now that we have scalar types turned on, running this. So as you can see, instead of concatenating the string, the PHP engine is now being smart and saying there's a type error where argument 2 passed into this function must be of type string. So we have something that's checking for the correctness of your code. You can see I can pass in type information and gain that extra level of support that the runtime engine can give me. But there's a lot of syntactic sugar that happens when you declare a function, and then underneath all of that there's an instance of this closure class, and that's going to be the subject of our next video. Welcome back to Functional PHP 7, and in this video we're going to be learning about the closure class. It's important to understand for functional programming that functions are first-class objects, and this means just that a function can be treated just like any other variable, any other object. You can assign to them, you can pass them into functions, you can return them from functions. In fact, behind the scenes, functions are nothing more than instances of a closure class. This was created back with PHP 5.3 to support anonymous functions, which later on we're going to be calling just lambda expressions. But functions, because they're instances of this class, they have methods of their own. And so this is going to allow us to do things like bind a function to an object. I'm leaving you here with this RFC about arrow functions, so you can check it out on your own, and you can see the progress of how this RFC is going to be implemented in future versions of PHP. Let's examine this piece of code. The objective of this program is to map a function over an array. In this case, we're mapping a function over the array 10, 20, and 30. The mapping function, here this we call a callable, is an anonymous function because it lacks no name at declaration time. But one of the most important qualities of this function is this use keyword, which is essentially bringing the factor variable into the function's closure. So when we map this function over the array, we apply a factor of 10 to each of the items, and we get a new array with elements 100, 200, and 300 respectively. A closure is essentially a lexical scope formed around the function declaration. So this means that when the function is declared, everything outside of the function is in the function's scope. So in this case, outer function sees all of the global data, as well as any arguments provided to it. Now, I'm returning a function within that function. And so function scope get inherited. So the inner function sees not just everything in the global scope, but also everything in the internal function's scope, as well as any other arguments that are provided to it as well. Using this internal closure type is what gave rise to anonymous functions back with PHP 5.3, and this is what it's also going to propel the use of lambda expressions going forward. Now, PHP 7 doesn't have lambda expressions implemented, it's only an RFC at this point, but if it did, this is what it would look like. So in this case, we're mapping a square function over each element in the array, and then we're using array reduce to go ahead and add everything up together. So in this case, the mapping function here is an arrow function that takes every element and computes a square function. That array is then passed into reduce, and reduce applies an adder function, another arrow function that takes two elements and adds the results together. So essentially we're mapping a square function and then we're reducing with a adder function, a map reduce combination that's very typical of functional programs, and the result is 55. The first thing we're going to do is prove to you that functions are in fact instances of closure. And the way we can simply do that is by printing the output of a function reference. So running that code, and you can see that PHP basically prints object of type closure. Remember earlier that I said that a function is a closure that can use to bind to other objects. So consider this simple use case. I have an abstract class called shape that has width and height. And I have two concrete implementations of shape. One is a square that you can assign to the length of a side, and it will assign to width and height appropriately. And the other one is a rectangle that can be instantiated with width and height. So print area is a function. It's actually an anonymous function because it has no name. As you can see, it's a first class. Functions are first class, so I can always assign a function to the print area variable. And when I call print area, it's basically going to print the width and the height of whatever object is passed into. Now, what does that mean? Because this print area is an isolated function, is not really part of any class. Well, I can bind an instance to this function and make it a method. So in this case, when I bind the square, an instance of square, that will basically resolve to whatever this points to within that function. So when I call print area, what it's going to do is it's going to access through binding that object into the closure, is going to access the width and the height properties. There's a shortcut that I can use where I can bind and call at the same time. So in this case, I can bind a square object, or I can bind a rectangle object, and print area will resolve this object accordingly. Okay, so now we can run this code and see the output. So as you can see, the area of the shape was 100, that was that first call, and then the area of the square was again 100, and then the area of the rectangle was 6. Understanding the foundations behind PHP functions is crucial to understanding higher order functions. Hello and welcome back to Functional PHP 7. In section 1, we took a brief crash course to examine some of the new features present in PHP 7 and how those are going to be used to make our functional code a lot better. In section 2, we're going to address the next question that should be top of mind, which is, why should I consider functional programming? If you already do some level of object-oriented code or have been doing it for many years, then the first question should be, why should I consider learning something new? And that's what we're going to try to tackle in this section. Now, as crazy as functional programming might sound, especially in the PHP world, ironically enough, it does do a good job at tackling the non-functional requirements of our application. Functional code tends to be easier to reason about when you're looking at solving the global scope of solving a problem or troubleshooting an issue. It's also going to lead to code that's easier to read and more succinct. The modularization imposed by composition will lead to code that is easier to test. And when you have protection around immutability and side effect free functions, it also makes code easier to parallelize. Now this last concern is something that we won't be addressing in this course, but we will be focusing on the first three, and it's definitely something to keep in mind if you wanted to take your functional programming skills onto a different platform. In the first video of this section, we're going to learn the meaning of writing code that is easier to reason about. You've probably heard this term a lot. Functional programming makes code easy to reason about. And what does that really mean? It really has to do with lessening the cognitive load, which means the amount of information that you have to keep track of at any point in time when you're looking or trying to solve a particular piece of code. And this has to do with, are you having to keep track of the state of many variables at once? Are you uncertain about a function's effects, not just to the particular function call that you're doing, but does it have any effect? Does the effect ripple out into other modules of the system? And functional programming really solves this in two ways. One is by eliminating side effects, and the other one is by promoting this idea that programs have to be immutable or stateless. So eliminating side effects is about providing what a function needs to carry out its work and making that available as arguments. So in other words, functions don't need to reach out of their own scope to carry out the work that they need and return and compute the return value. Because as you understand, if you're needing to reach out to other state, then all this global state becomes really hidden inputs into all your functions. And so, that's another way of increasing that cognitive load. The more global data you have, the more the probability of that data being mutated or changing inadvertently, right, by other parts of the system. And so we're trying to isolate that. We're trying to minimize the use of global state, keeping everything isolated into the function. The second principle of immutability is very important as well. And it just simply states that once a variable is declared, its value shouldn't change, okay? Now, PHP does have poor support for immutability when compared to fully functional languages or even to some other object-oriented languages that have keywords to impose different levels of immutability into your variables. We can do this one way or another in PHP. There is some support for it, but most of it will come out of discipline. And this discipline is really up to us as to what level we want to implement it. PHP will make it really easy to assign state into variables and mutate it. But the fact is that functional languages don't really have support for assignment. I mean, why would you assign to a variable if they're not even variables? They're not entities that are allowed to change. So typically in a pure functional program, the flow of a function happens it happens through composition. So you're calling functions and passing those as arguments to other functions, and they compose. And that's how the flow of a functional program moves forward. And the last two principles that we're going to learn about, the last two qualities of functional programs, are these ideas about equational reasoning and function level modularity. Equational reasoning is more of a theoretical view of how programs are composed together. So we talked about immutability and side effect free, and if our functions are pure and they have these nice qualities, then their output is going to be very predictable. Because remember, everything that a function needs to carry out its job will be given to it as arguments. And so if we can guarantee that the output of one of these functions, then theoretically speaking, we could replace a function call with the value that it produces into an overall expression, and the result is the same. And this is called the principle of substitutability or replaceability. You can replace a function call by its value in an expression, and the overall expression remains the same. The result is the same. And so that also helps that idea of programs being easier to reason about. And function level modularity is really no surprise. In functional programs, the emphasis is on the function itself, not on the object, although we know that functions are objects. but the main unit of execution becomes the function itself. And so the idea is that using functions, you're going to decompose big programs or bigger functions. This idea of the monolithic function goes away, and you're going to compose that, split it up into nice small chunks, and then recompose those together to form the entire solution to your problem. So when considering functional programming, you really have to embrace the idea of eliminating side effects at all costs. And some forms of side effects are things like sharing global data, writing UI or to a console or to an HTML page. Also database and file I/O operations. Throwing exceptions is even a form of side effect because the program has to unwind and the instructions flow is broken. And there are functional ways to address each of these concerns, and we're going to learn about those later on in the course. The most mundane example that you can think about when thinking about side effects is two functions that share data, and this is something that we do a lot. So consider the figure on the right where the first function do work runs and it causes a change into this global external data. And because it's reaching out to an external resource, this is a form of side effect. And then do more work runs afterwards, and it depends on that data. And so the execution of do more work is dependent on this global data being set. And so inevitably you have a form of coupling between do work and do more work. And so what we want to do is decouple these and make these isolated functions that don't depend on each other. So the other form is of making programs easier to reason about is this thing called equational reasoning. And so the idea is that we have a monolithic program, and you can imagine this to be any type of any big function. And through equational reasoning, if you have functions from one type to another type, again, they always return values. A program is made up from the combination of these functions, f, g, and w. But if these functions return x, y, and z respectively, then when solving this program, you could theoretically replace x to substitute for the function f, and the result of the expression remains the same. Okay, so functions and their values are replaceable or substitutable. And so now when we begin to extend all of these concepts into function level modularity and learn that the programs are made up of the sum of its parts, then now we can translate the theory into this concrete example where we take a function that computes, that reads the files for all the Nobel Prizes that are being awarded, and it finds the most decorated Nobel Prize category. Then we can consider this monolithic function to be the sum of much smaller set of functions, almost like a cooking recipe being followed step by step. And this theoretical model we can translate into a concrete model, into actual PHP code. And we haven't still seen how we're going to get there, but this is the goal of the first volume. And so we will be able to solve this example just like the function I've showed you here. If you take a closer look at this code, you really don't see where the actual execution is happening. Actually, all you see is basically a list or a recipe of functions that need to be executed to solve this problem. And that's exactly what declarative code is all about. The idea that we're going to look at functions in terms of what problem they're trying to solve and not how they're solving it. In this second video, we're going to learn about declarative programming. All functional programs tend to be declarative in nature. And what this means is that we're going to place more focus on building the structures and the individual elements that make up the solution to an entire program. Almost like this is very analogous to how Legos that individually don't carry much weight or don't really represent anything, but put together they can create really amazing figures. And so what this is all about is that we're going to clearly visualize the what and not the how of a program. So you get to see the individual pieces that assemble together to create the solution of a program, but really you have no visibility into how the state flows within it, how it executes. And so because we focus on these structures, then this leads to more reusable, succinct code, because now you have these individual Lego pieces that you can put together and create, and reuse in other places to create other types of solutions. And so when we start building small functions that solve our problem domain, what we're doing here is building a vocabulary or an ontology about the domain of the application that we're solving. This also favors the property of commutativity. In other words, we can create functions and that individually they can execute and they return some output, but we don't really care in which order they're going to be used. They can be used, they can be called in any order because these elements, just like Legos, right? They could be combined in any different way. Some examples of declarative programs are Haskell, SQL, things like regex, HTML, ML, etc. So here are a couple of examples. A regex expression is really a domain-specific language or a declarative program over the regular expression engine. So this particular regular expression here parses out the server path and the domain of a URL. So it does the whole process of tokenizing, extracting out all these pieces, but nothing from this expression tells you how to do that. In this second example, we see a simple SQL query. And what this is doing is basically providing a language over data lookup. And more importantly, it's also raising the level of abstraction when it comes to data operations. So instead of dealing with the internal loops and conditionals and data extraction and column matching and data matching and all these operations, what you deal with is a simple language over and a simple abstracted wrapper over all of that. Now, when we translate the declarative style of programming into PHP, it basically turns out to be just this, a set of function calls that will execute in a certain order, but none of this gives you any visibility into how the data flows within these function calls. And so this is called point-free style. The points in this case being the arguments. It's free of any direct explicit arguments to these functions. The arguments are being passed in through the orchestration that's calling all these functions, in this case pipe, which is like composition, and we're going to learn about that in a bit. But this resulting function, when called with the seed file, performs all these steps in that order. And so you get a sense of what the program is doing it just by reading the things that make up, or the Lego pieces in this case. Without a doubt, having your code be declarative and beginning to build internal DSLs that solve specific domains of your application is certainly beneficial. And in this last video, we're going to learn that functional programming is a lot more testable when compared to any other programming style. In this last video, we're going to see how functional programming leads us to the path of more testable code. Now, the reason we gain testability has nothing to do with adopting a test-driven development or a test-first approach. It has to do with putting the function as the central unit of modularity. So, in other words, functions are going to be the components that get passed around, called, returned from functions. In fact, one of the things that you're going to see in functional programs is that you tend to do a lot less assignment than do an imperative or object-oriented design. Functional programming also pushes the design of your application to have clear function contracts. And this imposes clearly defined inputs and outputs, which make your functions self-documented. And it also favors using strict typing, which we saw in section 1, so that you can create constraints between what gets input into a function and what comes out. And so when you start to use function composition, this will be really important so that you can make sure that the flow is exactly as you expect it to be. Also, a corollary from equational reasoning is this idea that functional programs enforce same outputs on same inputs. So your functions got automatic guaranteed assertion. They're never going to change. Given the same inputs, you're always going to get the same output, and that's always consistent. And that's part of the way functional programming is based on the math. Finally, at the heart of making things testable is this notion of no external dependencies. So functions are basically these isolated units of work that, like we said before, everything that a function needs will be passed in as arguments. So there's no reason for the function needing to reach out into its context to find any data or find any other resources. And this is also going to make them extremely easy to test, because now you have clear boundaries as to what the test inputs and outputs will be. And these are the principles that we're going to be applying to make this functional transformation. As we take large functions with lots of dependencies and we transform large monolithic programs or functions into a set of singular functions without dependencies that have clear inputs and outputs, and these much smaller chunks become much easier to test. And the reason this is due to a general rule of thumb that functions with smaller set of arguments tend to be a lot simpler. So the tendency towards singular functions means that the logic within those functions will automatically get simpler, right? Because if you can only work on the arguments that you're given, then it only stands to reason that the smaller number of arguments you have, the smaller the function's arity, then the simpler the logic will be underneath that function. And so it will be much easier to test as we approach singularity. Why consider functional programming involves answering some simple questions. Do you want your code to be easier to reason about? In other words, do you want to benefit from this mathematical quality that functional programs have? Data being immutable decreases the cognitive load of your program, and this is really important when you're trying to map out the state of the system when you're trying to run through troubleshooting a problem or coming up with a new one. Declarative coding raises the level of abstraction to define the what instead of the how, and this automatically raises the level of readability as well, because you're coming up with a vocabulary for your system, or almost a domain-specific language. Functional programming also makes your functions inherently testable by enforcing consistent results on the same input. This derives from that equational reasoning, and this will be a statement that we're definitely going to be pushing forward next as we go into the concept of pure functions. But just in general, when you treat functions as isolated black boxes, they're just much easier to compose, much easier to test as well. So up until now, you really haven't had the chance to see any functional code. We've been covering, first some PHP 7 basics, and now I wanted to really present a view of why you should consider learning functional programming without really getting into any of the details. And before we get into that in the next section, just an early disclaimer. So functional programming, just like any other software paradigm, doesn't solve all problems, and it's definitely not designed to replace or to be superior to anything else like object-oriented programming. While PHP 7 is an improvement towards writing functional code, it does lack a lot of the support that other languages have to make functional even easier. But in general, it's important to understand that whether the language allows you to do it or not, functional programming does promote sound principles and best practices to create robust and terse code, no matter the platform that you use. And keep in mind that functional programming and other software paradigms like object-oriented programming can coexist. So it's definitely not a question of should I choose one over the other, but more what types of problems present themselves better, coming up with solutions that involve possibly a hybrid of the two. So rest assured that while PHP is not a functional language, we will be getting really, really close to one. And that's what we're going to start doing in our next section, Fundamentals of FP. Hello and welcome back to Functional PHP 7. You've arrived at Section 3, Fundamentals of Functional Programming. And in this section, we finally leave behind all of the background and prep work and dive deeply into functional programming. In this section, we're going to define concretely what functional programming is. We're going to learn that it's really based on this pillar called the pure function, which ties into the referential transparency and correctness that we talked about in the Section 2. And then finally, towards the end, we'll compare and contrast the idea of using loops versus recursion, and hopefully in order to get you to end your imperative mindset. Now, this is not to say that you will never be able to use loops or even conditional statements, if then else statements and things like that, but you'll do so whenever practical without sacrificing the purity and the correctness of the algorithm. First, let's begin by defining what functional programming really is. Functional programming refers to the declarative evaluation of pure functions to create immutable programs by avoiding externally observable side effects. And so notice that I've taken the liberty to parse out some key terms here. We're going to look at code that is declarative, and you know what that means from previous sections, that is immutable, and that is free of side effects. But learning the definition of functional programming isn't enough. Functional programming is more about a state of mind that embraces statelessness. Now, it's still a general purpose paradigm in the sense that you can still solve all of the Turing-complete algorithms that you can solve with any other paradigm like object-oriented or imperative or structural. But the mind shift is leaning towards a mathematical reasoning, towards looking at functions as these rigorous mappings between one type and the other. And also leaving behind things like assignment statements. It's not that we're going to completely eliminate them, but in the immutable world, then there's really no need for mutations. Therefore, there wouldn't be a need to assign to variables. And so in that sense, you also eliminate loops because you apply that a loop implies that there's this counter that's constantly mutating. Functional programs are rooted on the notion of pure functions. These are the pillars behind this paradigm. And I'll continue to repeat this as many times as possible for you to understand that thinking functionally is about thinking in a world of pure mappings between types with no side effects, and that functions are really just references to a lazy computed value, some kind of representation of a value that doesn't change when called on the same input. So I'll continue to repeat these statements because it's important that we get really, really comfortable with this as we progress through this course. A distinguished fellow by the name of Robert Martin, who we know in the software community as Uncle Bob, for pioneering the Agile movement, among other things, wrote an interesting article comparing paradigms to each other. Now, this is by no means an exhaustive list, but it's interesting to see the effects of using a paradigm over a language. So for instance, Modular programming removes limitless files because now we tend to decompose things better and then join the results. Structured programming removes the goto. Object-oriented programming removes this concept known as function pointers, more in the C world, for inheritance and polymorphism. And then functional programming takes away assignment and mutable state. So it really comes down to which paradigm removes the necessary features to allow you to reason about your code better. With that said, let's begin writing code using pure functions. Welcome to video 3.2. Our natural point of departure into functional programming is understanding pure functions. In this video, we'll learn that pure functions have no side effects, that they can be treated as merely as black boxes with clear inputs and outputs, and all of this is rooted in the mathematical principles behind functional programming, known as morphisms, which are basically a fancy term for a function, and categories, which is a fancier term for the types of objects that we're going to be dealing with. Now, there's obviously no category theory required to understand this course, but it's always good to be aware of these terms. Some of the possible causes of side effects in a program involve reading from or modifying an external variable, especially global variables that come into the function. As we know, a global variable is basically now a hidden input into every function that you have. Changing the contents of an object or an array that's passed by reference, and so this rules out functions like sort that modifies the array in place. Those are kind of discredited from functional programming. Log into the console, writing to a file, reading or updating a database, throwing exceptions because that unwinds the program stack and breaks the flow of control of your program. So all these are considered side effects one way or another, and they involve basically reaching out to external resources outside of a function's scope. A pure function is also known in other languages or in other communities as lambda expressions. And the reason that they're known this way is because a pure function needs to be considered just a mapping between one type and another. So a pure function can be a mapping of object A to object B, for example. So it takes any element of type A, or if we go into category theory, we're saying any element of the category of A or the set, and maps that to an element of the type of B, right? So for example, a function that's like length that takes an array and returns back an integer is really mapping the types of arrays to the world of integers. But you can also have functions that are pure that map onto themselves. In fact, the function known as the identity function, a function that merely returns itself, it returns the input provided to it, is actually a requirement for a category to exist. In fact, this notion of functional programming being so heavily founded on mathematics dates back to the 1900s, founded by lambda calculus and Alonzo Church. And so lambda calculus introduces the notion of a function, actually an anonymous function that has no name. Everything is considered a lambda. And so for instance, the first expression is nothing more than an anonymous function to increment by 1. So it's a function, a lambda expression that takes some input x and returns back x plus 1. So it's an increment function. So if we use that increment function with the argument 3, we get back 4. So the lambda expression evaluated for 3 returns back 4. And then we can do a lot more complicated things. And here's when we're going to get into functional composition and where that comes from. But now you get the composition of two expressions. So you get a lambda expression over y that applies 2 to its argument. So if you evaluate the entire expression with 3, the first thing that executes is the rightmost expression. You add 2 to that, you get 5, and then the result of that gets embedded into the x argument. And then you add the 1 to that and you get 6. So basically this is really the birth of notions of functional composition and representing programs as being functions embedded within themselves without having any assignment. So let's learn about the identity function, which is the most primitive pure function. This function is very simple to understand. Any input that it takes, it basically echoes it back, it returns it back. But as you can see, it fulfills all of the FP principles in that it doesn't throw in exceptions, it doesn't rely on state outside of its scope, it doesn't modify the contents of any variable, so it's immutable, and it doesn't share any data and doesn't require any external dependencies. So really it fulfills all of the qualities that we want in our functions. As a lambda expression, it could be written using the arrow notation. And as you know, PHP doesn't have support for that. Currently, there is an open RFC, request for comments, to see if we can get that included into future versions of the language. While the identity function may not seem as much, it's actually an incredibly useful technique in FP. And we're going to use it in this example to clone arrays. So first I want to show you the object-oriented way of doing it. We're going to go ahead and create a fruits clone, and we're going to use the SPL array object class to wrap over the original fruits array. And then just to prove the point, we're going to go ahead and let's add another object into the clone. We have 4 pairs, and then we can get this copy. So to get the copy, we use a fruits clone, and we invoke the get array copy. So if we were to print out the copy, we would see that it makes a clone, and the original is going to stay intact. So let's go ahead and run that here. Okay, so you see that we added the pairs into the first array copy, but the original stayed intact, so that's a true clone. Well, seems like we're writing a lot just to do this. Let's do the functional way. So for the functional way, we can go ahead and create another clone. And what we're going to do is use this function called array map, which is incredibly useful because it's going to iterate over the array and it's going to map new values into it. And all we're going to do into this new array that gets created from array map is just simply map the identity function onto it. And because I'm using namespaces to group everything, I just have to take care of this idiosyncrasy of PHP and use the identity function. I'm going to map that over the fruits array. And it's as simple as that. So to prove it, we're going to go ahead and add the pairs to it. Let's add 8 pairs into it. And now we can print out this copy. And as we're going to see at the end, everything will remain the same. So you can see the original array always stayed intact. We were able to make a clone and add the 8 pairs. And we were able to do this in a much more succinct manner using functional programming and using the identity function. And this is kind of what you get with pure functions. They're very simple to use, but put into larger expressions, they solve a wide variety of problems. And now we're going to apply pure functions towards the problem of iteration. So stay tuned for our next discussion, loops versus recursion. Hi, and welcome to video 3.3, loops versus recursion. In this video, we're going to take a look at what recursion is, why recursion is the more natural way of looping over code in functional languages, and then finally, what advantages we get with tail recursion. A recursive function is one that can call itself, and this feature is present in all pure functional languages, but it's also present in PHP because it's a stack-based language. And this means that every function call gets placed in a stack, and it gets popped out when the return value comes in. When a recursive function calls itself, it calls itself on a smaller subset of the problem, or a self-similar version of the problem. If you think about the way you iterate tree data structures like HTML documents or XML documents, every node in an XML document looks structurally the same. But if you think about computing factorial or Fibonacci numbers, then in that case you can call the function again on the result that is closer to computing that factorial. A recursive function has 2 main tasks. One is the base case and one is a recursive step. The base case triggers when there's no input left to process, and so at that point the recursive function returns. The recursive step is the step that continues the recursion. In this, if you use recursion for looping, it's the step continues the looping to move forward. Now in PHP, there's a strict limit over how many recursion levels you can have, and you can easily blow out the stack if you exceed that number, which can be configured through PHP INI. Recursion is actually the more natural way of iterating in pure functional languages because you don't need any other keywords. You don't need for each, you don't need any other constructs like while and do while. You just use functions to accomplish all of these goals. Recursion also allows you to iterate immutably and side effect free by controlling the loop conditions via function arguments. And this means that if you're, let's say, computing the sum of all the elements of an array, you don't need to keep a global counter and a global sum that you're incrementing and constantly mutating to arrive at the result. You can just use it by passing pure arguments into these pure functions that are recursive. And the additional benefit is that, and these are concepts that we're going to learn about later on, is that recursive functions are actually memoizable and composable, especially when considering whether to use recursion or looping for iteration. There's one variety that sticks out called the tail recursive call. Tail recursion is optimized out by the compiler, typically in pure functional languages, and this is called tail recursion optimization. And it works for functions that are in tail position, meaning the last step of the function is actually the recursive step. PHP doesn't support TCO, and so what we're going to do is show you how we can use a trampoline, which is an artifact that we're going to use to simulate tail call optimization. We're going to provide the optimizations ourselves in userland space and overcome the stack limitations. The way TCO works is essentially we're going to take a tail recursive call and add some scaffolding code so that we can flatten it out into a loop that can execute indefinitely and we don't have to worry about any stack limitations. Okay, so let's see how we can use functional programming to emulate and solve all the same problems that we solve with iteration. So I'm going to continue building on the identity function, and we have array clone here, as you can see. So what we're going to do here is our exercise is to loop through an array and add all of its elements. Now you can do this easily with the for each loop and keeping a global counter, and mutate that global counter, increment it by adding every other element that you encounter in the array, and at the end you get the result. But we want to do things immutably. We don't want to be changing state all the time, and certainly loops and global counters are out of the question. So we're going to use recursion. Our array add function takes any array and it's going to return a float, which is a result of adding all of the elements in the array. And we're going to do this recursively. So what we want to do is, with recursion, is always useful to create a facade for your calling code and internally take care of all the iteration logic. So we'll do a recursive add that internally will call with a clone of the source array. And we do this because we want to avoid, again, mutating the original array. So it's always beneficial to create copies of these data structures so we can leave the originals intact. Our internal recursive function, and in PHP we can embed functions into other functions, has the following signature. It takes an array and returns the float. Very similar signature to the one above, but this gives us a chance, by creating a facade, it gives us a chance to create this clone. So the function rec, the first thing we're going to do is create our base case and then create our recursive case. So the base case is that if the array is empty, we return 0. In other words, adding all the elements of an empty array is 0. Otherwise, we popped the elements out of the array, and we implement this concept that's used a lot in functional programming, is this notion of a tail and a head and tail of the array. So we pop the first one out and add it to the recursive call of the rest of the elements present in the array. And so you see, in order for us to use these PHP functions, I needed to create this clone, because array shift will change the structure, the contents of the original array. So it was important that we added this clone, and now I can always shift, pop that element out, and add every element to the rest of the array. We can run this function with a sample array of all the numbers 1 through 9. As you can see, I required the array add function, and then we're going to add that into the result and print it out, and also print out the original so that you can see that the original source array stays unchanged. So running our first program, as you can see, we were able to add all the elements in the array, yet the original array stays unchanged. Okay, so for our next example, we're going to show how to do the factorial function done recursively. By definition, the factorial of a number is the multiplication of all the digits from 1 to that number, all the integers from 1 to that number. So the factorial of 6 would be the same as 1 times 2 times 3, which is 6. Okay, so again, we want to keep that easy to use facade. Underneath that, we want the recursive logic. So internally, we know that recursively, we need to compute the product of the numbers from 1 all the way up to n. So we have that concept of that minimum and that maximum, and we know that that minimum needs to be incrementing as soon as it reaches n. Okay, that's when we stop. So what does this product function look like? So the product function will take a minimum, which starts initialized at 1, up to a maximum, which is initialized at n. We know that we also need to be able to compare it with the number that we want to compute the factorial for, so we're going to need to use that function. And because we're going to call ourselves recursively, we need to feed that variable back into the function, right? We need to feed the product function variable itself to be present inside of the closure so that we can call it again. Okay, so that's the layout of what we're looking at for our function. Okay, so our logic proceeds as follows. Remember, the concept of min is the number that's going to be incrementing up to n, which is max. So our base case is going to be that if the min matches the number we want, so in other words, we've reached there, then we return the result. We return whatever max holds, because that means that we're done, that we've computed the multiplication, which is held in max. Okay? So if that's the case, we return max. Otherwise, we perform the computation of the minimum and up to where you're at. And because these numbers can get pretty big, we're going to be using the BC for addition and precision multiplication. And so what I want to do is recursively return the product of what's going to become my new minimum, which is the BC add the min plus 1, we're incrementing to the next integer. And then the next function is the multiplication. So BC multiply min times max. And one important detail of this implementation is that we need to pass the variable function by reference. Passing it by reference, because we're declaring it in the same line as when we're using it, we need to pass it by reference so that it's available to use. It's available in the function's closure so that you can call itself. So let's go ahead and echo this out. Print the result of factorial 6, and this will be factorial of 3. And running that prints out 6. And let's keep on playing with with bigger numbers. So let's try 3,000. Factorial of 3,000. We'll run that again, and it computes. It's a very, very large number. But let's see what happens when I add another 0. Adding another 0. This is a factorial of 30,000, an incredibly big number, and we run that. And effectively, we've been able to blow out the stack. In other words, we've exceeded the amount of calls that we can make recursively. So we must be able to iterate through large collections of data, otherwise the FP paradigm will be at a disadvantage. And we need to be able to get around PHP's call stack levels, otherwise we wouldn't be able to use it recursively and functionally. The way we do that is using a trampoline. A trampoline is an artifact that takes any function and the arguments that the function operates on, and the gist of it is that it's going to always call the function until it has arrived at some value. In other words, it takes a function that can be called recursively, and so long as that function continues to return back a function, then it's going to continue to call it through a loop. Essentially what it's doing is it's flattening out the recursive structure into a loop, which we know can execute indefinitely. And as soon as it arrives at a value, in other words, not a callable, then it returns. The trampoline only works with tail recursive calls. So in order for this to work, our recursive function must be in tail form, and it is, because tail form means that the last statement the function executes is a recursive step itself. So in order to make this work, all we need to do is wrap the recursive step into a function and let that function return the result of calling the recursive step. So we're just going to defer it. That's essentially what we're doing. We're wrapping it in a function so that it can be managed. This function is going to be using all of the data. We need to bring that into the closure, and that involves the product function itself, min and max. And the result of this calling this function is just to return the recursive step. Okay, so now that we've wrapped that function there, we can use a trampoline to control the result of the factorial and essentially flatten it into a loop. We'll apply the 30,000 number and run it with that. So this actually took some time to run, but it came back with this incredibly large number. Using trampoline functions yourself is not something that you would typically do in a pure functional language. But as we said at the beginning of the course, PHP is not a pure functional language, so we have to create some artifacts to make it act that way and to enable the FP qualities to come out. But essentially, a tail recursive call can be optimized out by this function and flattened out into a sequence of calls until the base case is reached. That's essentially what we're doing here. In the next video, we're going to decompose an imperative program and transform it into a set of smaller pure functions that are going to be composed together to arrive at the solution. In this last video, we're going to look at transforming an imperative program into a functional one. In this video, we're going to be writing code to decompose a function done imperatively into a set of smaller pure functions, and then we're going to compose those pure functions to solve the program as a whole. And this section is one of my favorite ones because it's basically all code. So let's dive in. This small program has a couple of dependencies. One of them is a database. And so for this program, we're going to be using a simple composer library that is a thin ORM layer called Illuminate. And you can install it by adding the Illuminate database package. And then using it is very simple. Once you've autoloaded all the classes, you add the connection information to your local database, and then just a basic configuration. I have a local database installed, and the table that we're going to be reading from is the users table. So we look at the contents of that table. We have 4 records with 4 users. Each of them has an email. Okay. The second dependency that I have is a user class, which I'm going to use to model every single row of that database. So the user class has defined 4 properties representing each of the columns of the user table. So it's a simple user class with getters and setters, and it uses this static hydrate method so that we can always hydrate a user object from a database record. This hydrate function creates an instance of the user. It extracts all the variables from the MySQL database record, and it uses it to create and populate the instance of the user, and it returns a user. So we're hydrating from a database record to a user object. So our task is going to be to read a user record by ID from the users table, and then modify the email to generate a new email for this user using some random behavior. So this will be the problem done imperatively. We have a counter object that keeps track of how many emails we've generated. It's a global variable that we're bringing into the function. We're also reading using the Illuminate Database ORM library. We're reading the user table for this user ID, and we're extracting that first record. If the record, we do some validation. If the record is not empty, then we proceed to hydrate the user object. And the new email is going to be a hash of the first name, the first character of the last name, plus this unique counter at packt.com. That will be the new user email. And then finally, we return that email. Okay, and if the database record is not found, then we return an invalid argument exception. So we're doing some error handling as well here. So running this imperative version picks out the user2 by ID, and which is Luis Atencio, and then it goes ahead and generates a new email for Luis. So the pure transformation here, the functional transformation, the first thing we need to do is decompose a problem domain into some fine-grained functions, into some pure, smaller, singular functions. And so we've recognized that in the imperative version, we have a few tasks to do. We need to be able to find a record from the database, right? Given some kind of user ID. We need to be able to validate that that record actually exists, otherwise return some kind of exception. Let the client code know that the ID is invalid. And then finally, we need to be able to generate an email from a user object. So that's a function that would take a user and this counter and gives us back an email string. And then finally, once we have all those steps defined, then we need to use composition. We need to compose those things together so we can arrive at that same solution. Let's begin with find record. So the function find record is going to take a user ID, which is an integer, and it's going to return back an instance of this PHP std class, which is basically it's going to be a dynamic object. And we're going to use our database helper to query the users table. We're going to be querying by that ID, and finally query that first record that comes back. Okay, so that's find record. It's just a function, a pure function that takes the ID and returns back a database record for that ID. Next, we're going to do the valid function. You can also call it validate or isValid. Essentially, that function takes any value and it checks if that value is not empty. If it's not, then it's going to return that value. If it is, it's going to throw a new invalid argument exception. And we're going to be saying user not found or some hard-coded message at this point. We're not very concerned with the error handling at this point. And we also recognize that, remember from previous discussions, throwing an exception is a form of side effect, and we're going to be slowly dealing with that in a functional manner as we proceed through the course, but for now, we'll just accept this form of side effect. So that's the valid function. And finally, we have generate email, which is a function designed to take a user object and this unique qualifier and return back an email. We'll call it generate email, and that will work on a user object, some kind of qualifier integer, and return back a string, which will be the new email address. And just like before, we're going to return the implode of the pieces of the email, which are formed by extracting the user's first name, last name, actually the first character of the last name, as is typical for companies to do. And then we'll inject this qualifier to make things unique. And then the final piece is the domain at packt.com. So that's our generate email function. So now we've decomposed the problem into these smaller, pure, easily testable functions. So here's where the fun begins, because an imperative program, you approach it from top bottom. That's the way code executes, right? So your mind naturally reads it that way. You acquire this counter, you read the record, you validate, you hydrate the user object, and then you compose, put together this email address, and you return it. It's really a top-down flow. But when you think about functional programming in the sense that you don't have the luxury of assigning and doing much assignment, I mean, we will be doing assignment, but it's typically not a practice of functional programs. You have to approach it in a slightly different way. And the way we're going to do it is by thinking of the program in terms of layers, in terms of peeling an onion from inside and out. Let's go ahead and put all this together. So our email output will come from the following program. So at the top level, we need to be able to generate an email. That is the purpose of the program. So we'll start there. We know we need to generate an email, and we know that email has two parameters. One is the user object, and one is the unique qualifier. So for the user object, we know that the user object needs to be hydrated from a database record. So we know that we need to go ahead and hydrate the user object, and so we'll invoke that function. And then the second argument would be the unique qualifier, which we can use the PHP 7 random int, which is a cryptographically secure random number from 0 to 9. So what goes in here? Well, what we need to do to populate that user object is to find a valid database record. So then the first thing we're going to do is, we know that we need a valid record, so we'll validate the result of fetching a record with ID 2. Okay, that's essentially what we're doing. You see, we're approaching the problem from as if we were peeling an onion from inside and out. So what we're doing here is, you can see that we have zero assignment happening. We're generating an email based on a user object and a random qualifier. That user object is made up of invoking the hydrate function on a valid record with user ID 2. Let's comment our print so that we can run the functional version of that. And as you can see, both the imperative and the functional program return very similar outputs minus the unique qualifier, which is a random number. And yes, the random number is also a form of side effect because it's essentially a non-predictable number, but it's pure in the sense that you request a number and you always get one back. Now, it's not referentially transparent, but it's something that we can always use in practice. At a glance, you can see the significant difference in style, right? The functional solution uses much less side effects in the sense that we're not importing a global variable anymore, and all of the how has been completely abstracted out into pure functions, so that you can only see, from reading this program, you only see the what it's trying to do. Generating an email, hydrating some user object based on a valid record from the database with ID 2. It's really easy to read and follow what's happening. And you can see the structure of these nested functions, and that's the structure that functional programs tend to have. Very little assignment, and it's more about moving the user flow forward by invoking functions. This was your first real exposure to a functional program. I hope you enjoyed that code as much as I did. And so now let's recap this section. So we've decomposed the definition of functional programming. We've parsed out and explained all the main terms and the main definitions. We've studied the root of the entire paradigm based on pure functions. That's what we've been focusing on for the majority of this video training series, and that is the foundation, the pillar of functional programming. We've also compared the differences between loops and recursion and see why functional programs favor recursion, because it's based on functions, so we always want to be able to call and use functions. And finally, we've decomposed an imperative function, and we showed it done imperatively, transforming that into a easy to reason about pure functional program. In the next section, we're going to continue this theme forward, and what we want to do is move towards function composition. And so the next topic that we're going to look at is function evaluation strategies. Hello everyone, and welcome back to Functional PHP 7. In this section, we're going to be learning about function evaluation strategies. In this section, you're going to learn about 3 fundamental techniques, all related to functions. The idea of lazy versus eager evaluation, a technique known as partial function application, that then leads to the basics of function currying. Let's begin with the first video titled Lazy versus Eager Evaluation. Because PHP is not a natively functional language, functions are executed immediately regardless of whether the result is needed or not. In other words, PHP only supports eager evaluation, and that means that a function gets executed as soon as it's seen by the interpreter. On the other hand, functional languages like Scala and Haskell support lazy evaluation by default. That's just the inherent mode of executing functions. And so functions are executed only when the result is needed. However, using higher order functions, we can emulate this idea of deferred or lazy execution. And whenever we run into some issues, particularly with processing collections, we can always resort to iterators and generators in PHP to kind of emulate the idea of evaluating collections or infinite collections lazily. Let's jump right into the code. In the previous section, we took a look at a function called generate email, which would take a user object and a random integer. Now, whether that user object was needed or not, this entire function or this entire composition of functions always ran because PHP is running functions eagerly. Now, suppose that this function random integer was something a little bit more complex and it actually produced an exception or some invalid number that we were checking against. Suppose we had an if-else statement inside of generate email that would check against this random number, and if it's out of bounds or if it's negative or 0, we wouldn't generate the email at all. We would just return back an error. Regardless, the user object was still generated and this entire code still ran. Let's take a look at another example. Suppose I have a function called multiply with or multiply by, and what this function does, we'll get rid of this code, and what this function does is it takes an integer just to keep things simple, but what it's going to do is going to return back a callable. So let's go back to that use of higher order functions that we learned about in previous sections. The function that's going to return back is going to take another integer, and finally this will return back the int. So in other words, the result of the multiplication. The inner functions uses a, so we bring a into the inner functions closure, and then finally we compute the multiplication of a times b. So why we would do something like this, and why not directly multiply a and b and just accept both parameters? Well, because deferring evaluation has a lot of benefits. I can always make an assertion that a function make even, I can make this function, I can create this function by doing multiply by 2. So multiply by 2 is a function that runs, that returns a callable, and that callable goes into make even. So make even is a function created from another function. Now this function hasn't run. This function the function pointer is stored lazily into make even. And in fact, because multiply by is pure, then we can say that multiply by 2 represents a pure number, a pure representation of all the even numbers. In fact, I can go ahead and assert that 4 would equal make even of 2. This assertion would always work because make even 2 is a pure representation of the number 4. In other words, we say that a pure function is a lazy evaluated number, is a lazily evaluated value or collection of values. Now, what can I do with make even? Because I have a function, a variable function stored in make even that's lazy, it's a function that's dormant and it's waiting to be executed, I can always do some very nice things. So suppose I want to map make even, and notice that even though PHP is eagerly evaluated, this function is not executed yet until the expression is executed, and then I want to map that function over a simple collection. So let's see what happens when we run that. And as you can see, I was able to successfully map the function make even over the array 1, 2, 3, 4, 5, effectively getting 2, 4, 6, 8, and 10 in a completely new array. Hopefully that example shows you the benefits that we can get with lazy evaluated functions. But that's not the end of the story. Consider this example. We'll use the PHP function range to create an array of elements 1 through 5. And when I run this, this basically prints out this array. And what I want to do is say this function doesn't exist and we'll create it. But what we want to do is basically take a slice of that. So we're going to go ahead and take from this source array, we're going to take 2 elements. And when we execute this, we expect to return just 1 and 2. So we've basically taken the first 2 elements. And so because PHP runs eagerly, the range function will run to completion to satisfy this variable, right? Even if I were to embed this function in here directly, and then apply array take. And if we were to implement this function, we could use array slice to do this. So array take is a function that takes an array as input and the amount of elements to extract, returning back another array, of course, and this function is just basically taking a slice of that array from 0 offset to that amount. So that's essentially what array take looks like. And so what would happen when we do something like this? So this would work, and this would print out elements 1 and 2. But what happens when we do something like this? We create a huge array using range of all the elements from 1 to PHP's max integer number. And then we take 2 elements from that huge array. So this actually wouldn't work, because what would happen is that because PHP's functions are eagerly evaluated, the range function, let's say that I would embed it in here, the range function would like to run first until completion before array take gets a chance to run. So what this is going to do is completely exceed the stack. It's going to blow off the stack when trying to create an array of such an enormous size. In a lazily evaluated language, the result of the range function would be used only when required. And so even though we would execute a function to create a range from 1 to infinity, infinitely many elements, we would only take 2 of them. So the resulting array would actually be an array of 1, 2. And in a functional language, this would actually work. Well, we can actually make this work by using some PHP 7 features. In particular, we're going to be using this feature called a generator. A generator is essentially behind the scenes an iterator object. And so what we can use it to lazily process or iterate over infinite amounts of data. So the way we're going to do it is we're going to first refactor the range function, and then we're going to refactor the array take function. Let's begin with the function range. So we'll call it xRange, so that not to have it confused with PHP's own range function, but the interface is going to be very similar. It's going to have a start value, the end value, and this optional step value that indicates how the array values would accumulate. But instead of returning an array, this function would actually be returning our iterator or generator object. Generators in PHP are very well designed to work with for each loops. So even though that's not the preferred construct to use in functional languages, it's something that we need to do just to make use of, to do the best practices of what PHP puts in place. So our range function can run a for loop that starts at the start value, it increments all the way to the end value, and here's where the power is. Instead of returning the functions, we're actually going to yield a value of I times the step. The step indicates how it accumulates. The yield function indicates or signals to the PHP interpreter that this is actually a generator function. So what it's going to do is that it's going to do a reentrant function. In other words, the yield pauses the state of the generator where it is. It pauses the state of all the variables so that you can always come back to it. When the generator function is invoked again, it remembers the state of all the variables that were in it, and it can recreate that and yield the next value. Array take needs to be refactored to take advantage of this generator. So array take, instead of working over an array object, is going to work over a generator, which we'll call the source. And of course, we'll need to know the amount of elements to take from this generator. And the output is an array of just the elements including up to the amount. Again, generators are designed very well to work with for each. So we'll start with that. And then for each value in the source, we will create a temporary function and store those values in there. And if would go all the way up to when we've picked up or collected the right amount of values, and at that point we can break this logic. At the end we return the result. So the generator function behind the scenes is really acting as an iterator, putting it inside of the for each loop, treats it as an iterator behind the scenes. It's invoking the next method on the iterator and giving back all the elements in that source generator. And now I can make this work just like the other example. So what I want to do is array take of the xRange from 1 to PHP int max, and we're only interested in the first couple of elements. And so now instead of running eagerly and taking up all the space in the PHP interpreter runtime, it's actually going to just take the first 2 elements. The generator will run up until where it needs to and not further than that, according to our logic in array take, and only return the first couple of elements, or we can take the first 2, 3, 4, or 5 elements. Let's see how this code runs. Voila, and this is actually the result we expected. And here's one last example to kind of drive this point home. Because lazy evaluation is not just a matter of convenience or a means of iterating over infinite amounts of data. We can also use it as an optimization. So consider this refactored version of range, and we call it drange for a deferred range. And it has the same front-facing API with the start, end, and step, but instead of returning at the generator directly, I'm returning a callable. And so when you see that a function has this return type, you can pretty much understand that this is a function that is deferring some kind of computation. Okay, so now it's returning a callable, and the callable is what actually runs the body of code. But as is right now, if you call drange with all the parameters, it just kind of sits there and wait. I'm also going to be using this function average, and this just basically does the sum of all the elements in an array. This is completely eager, divided by the count, and it returns the average from an array of numbers. Now, if I were to write a function that compares the average, it kind of does an assertion, and I would use the average of the range of numbers from 0 to 10 and run that computation, then this function would run eagerly, right? It would first run the range function and then use that to run the average function, and then pass it on to run the compare average and make sure that those two numbers match. But what happens if I pass a null or something else here? Why would I ever need to run all of this stuff to then later throw it away? So we can actually create a compare average function that uses lazy evaluation as an optimization. And what it takes, instead of using the array directly, it's going to use the callable that led to the generator. So this would be an array generator. And it's going to use that other number similar to what we passed before as the comparison value. So we're going to compare that running this average compares to that value that we pass in. And if it does, it returns true. Otherwise, it returns false. So this is really nice because, see, I can do all of my upfront logic and check if the comparison is less than 0, throw an exception. Otherwise, run the average function with all the data contained in the generator. So, with returning a range of 0 to 10, this is probably not a big deal. But if you wanted to take the range of 0 to PHP int max, or some other long-running computation, then this would be a very big deal. That you would just do run all this, compute all this data to then just throw it away. So after the comparison is true, remember this array generator here object, this object is still dormant. It hasn't actually produced any values yet. So I'm using this nice PHP iterator to array object. This basically does all that for loop, just like we did before, and converts the generator function into an array, takes the average of that, and then compares to that comparison. So the final result, when we compare average to using the D range of from 0 to 10, compare that to 5.0, that assertion is actually true. And we can test that by running mean, and there you go. The fact that the exception didn't fire means that the comparison was successful. All these concepts that you learned, you can see that lazy evaluation can be used not only to represent a pure value or a collection of pure values via a function, but it is also an optimization technique, whether you want to process an infinitely large collection or whether you want to do some lazy loading to avoid having to compute unnecessary functions. In the next video, we're going to take a look at this concept in a whole new way and learn about partial function application. Hello and welcome back to Functional PHP 7. In this section, we take a look at partial function application. What is partial function application, or also known as partial function evaluation? It's very similar to what we did in the previous section. If you remember the multiply by function where we decided to apply the first argument eagerly and then return back a function that waits for the second argument, in a way that is what partial function application is. It's the ability to invoke a function by providing just a subset of the function's arguments. And so what you get back is a function, another function, that expects the rest of the arguments to be provided. In this video, we're going to be taking a look at the partial function. In other words, this is called automatic partial. It's a helper function that we can use to wrap our functions and provide this partial behavior. And this is going to lead to the foundation for understanding what function currying is in the next section. What this function does is take a callable argument and a variable number of arguments that we want to partially apply. And what you get back is another function that awaits the rest of the arguments to be applied. And so the way it does this is by dynamically invoking this function with the rest of the returned function's arguments. I know it sounds like a little bit of magic, so let's see how this works. Suppose I want to create a function called multiply, just like I did in the previous section, multiply by. Now in this case, I won't use the technique of returning another function. I'm going to go ahead and type the function just as I would normally do it. And the multiplication of two numbers returns, that is A, returns A times B. Similar concept to before. But now I want to partially apply just A. So I can make any number even. I can multiply any number by 2 using the partial of this function. And because I'm under a namespace, I just have to get through this language idiosyncrasy, call in multiply by with the number 2. I'm partially applying the number 2 into the argument A. And so what I get back is another function that is dormant. It's lazily evaluated, and it expects the argument B to be passed in. First of all, let me prove to you that this actually works. So I can actually assert that for is exactly the same as applying the function by 2 to the argument 2. Again, this argument is the argument that goes into B. And if that fails, I'll return a new runtime exception indicating that validation failed. And so if I run this test and no exception comes out, I know that the test succeeded. Let's go ahead and give that a try. And as you can see, everything worked. But let's move on to a little bit more complicated example that involves processing a collection of items, just like we did before. And so I can use array map to take this function and lift it over the set of numbers from 1 to 5, or I can also do, just like we learned before, I can also do the range of 1 through 5. That would generate an array. So I'm mapping the function to over the range of numbers 1 through 5. And let's see how that runs. And as you can see, I was able to get the exact same array as the first section, right? Mapping over 1, 2, 3, 4, 5, mapping a function that multiplies by 2 generates an array of 2, 4, 6, 8, and 10 respectively. But I don't have to stop here. I can continue to partially apply functions. So I can try this. Map by 2 is just the partial application of array map over the by 2 function. Now what I'm doing is I'm going to be mapping the by 2 function over array map and partially applying that, so that array map by 2 is a function that now just waits for the array to map over. So I can just go in and print r, and now I can simply do map by 2 of the range from 1 through 5. So let's go ahead and run that. And as you can see, I get the same exact result as before. The partial function and its cousin operator, the curry, which we're going to learn about in the next section, can be really compelling when it comes to injecting dependencies into a function. In other words, what dependency injection does for classes and objects, partial function application does it for functions. So if you recall our write to file function that we used earlier, write to file was a function that took a path and the contents to write. It was roughly something like that. Well, then you can always create a writer function. And what we can do is partially apply the path to write to file. And this can be something like section 4.2.txt. And now what I get back is a writer function that's ready to write the contents of anything that we want to write into that file. So this writer function is ready to take in and write and append any content onto that file, just like that. I don't have to continue to define this path any longer. And so it's a way of injecting that dependency into the function and getting back a function that's ready to be used. Now that you understand the inner workings of partial, this will be enough to understand what function currying is all about. Hello and welcome back to Functional PHP 7. In this section, we take a look at currying, which is one of my favorite functional techniques. Currying together with functional composition that we're going to learn about in the next section, or absolutely everything you need to begin writing functional code. So I'm very excited to get here. Let's begin with what function currying is. It's a way to evaluate function arguments partially and return new functions. I hope that's ringing a bell by now. Once you provide all of the arguments to a function, then the function actually computes. That's very similar in many ways to what partial is, except that the difference is that currying transforms a multi-argument function into a stepwise series of singular functions. So in other words, if you have a function of a, b, and c, for example, then that's going to be transformed into a function that waits for a, then b, then c, one by one. So you transform a function of a multi-arity function into a singularity function. And this really enhances API design. And we're going to see the example of constructing and implementing our own logger toolkit. But the most important part is that currying is a necessity. It's actually a necessary tool to implement function composition, and that we're going to get into in the next section. The curry of a function is actually something very simple to understand when you look at it visually. So imagine a multi-arity function, a function of 3 arguments in this case, and we want to compute the curry of that function. Just like partial, curry returns another function which we call f. Evaluating f with 1 argument, in this case a, returns back lazily a function that waits for b and c. If you evaluate the function with a and b at the same time, then it returns back a function that it waits for the function for the parameter c, for the argument c to be provided. In other words, with curry, you will never be able to invoke a function with a subset of the arguments. You will always have to pass all the arguments that it needs. And then as soon as you evaluate the function with a, b, and c, then the function actually runs and then the body executes. Just like with partial, one very important aspect to take into account when currying functions is the ease with which a function can compose. Now we're going to learn about that more in the next section, but functional libraries like plambda, for example, They are optimized for currying. And that basically means just what I said before, that you place the most dynamic argument at the end of the function signature. In other words, the parameters that are more fixed are placed first so that you have the opportunity to curry or partially evaluate them. And then the part that always changes, the part that is dynamic, is the one that's placed at the end. And so you will always want to optimize your function for currying. And it's just simply placing the dynamic parameter at the end. So in this case, if we build a simple logger function and you want to have it where you can specify the resource or the file that it's going to go to, the level of the logging level, debug, trace, info, warning, etc., and then the message. You want to optimize it that way because the message will be always the dynamic argument. You always like to fix the path and the level so that you can create debug loggers or error loggers and then just pass the message in. In other words, this is optimized for logging. Otherwise, if level is at the end, will hardly ever be the dynamic argument in a logger. So you always want to place the message argument last. Let's jump right into the code. And before I show you a manual function curry, I want to build a quick API that I can use to showcase this concept. My API is also going to use partial, so we're going to actually be mixing in partial and curry, and everything is going to work in beautifully. Partial is just like before. It takes a callable and a dynamic variable number of arguments, and it returns another callable as a function that expects now less arguments. I'm reiterating write to file just like I mentioned in the previous section. That takes a path and the contents of what I want to write. And as you can see, I'm no longer returning a function. I'm actually just writing to the file itself. But I'm using partial to simulate that deferred loading, that deferred execution of the function. I'm passing write to file, and I'm also partially evaluating the file name that I'm going to use to write all of my logging, right? So I create a file logger. And I do this because I want to have the option to use a file logger or a console logger. A file logger goes to a file with this name, and the console logger just merely prints to the console. And my API is very simple. My logger function is a function that takes a function that expects a string, so it's a callable. It takes a string level, and it takes the message that we want to log. And the way it logs it is that it basically uses whatever resource is passed in, and it formats the logger with the level and the message. And that's all it is. All right, and let's see how I can use this logger function. The logger function expects 3 arguments. Let's say I want to write to the console log at a debug level, and I want to say this is a debug message. Right? I provide all 3 parameters. I can also alternatively say, let's write to the file log at a debug level. This is another debug message. So every time I call the logger function, I have to always specify these 3 arguments. Let's see how this runs. And as you can see, the console log logger came in, and in the file, I also have, this is another debug message. Okay, so that's definitely working. But having to specify all 3 arguments every single time I use the logging function is very cumbersome. So let's create a version of the curried logger. And the curried logger is a function that's going to take our resource, which is a function of string to the empty set. It's a string, it's a function that prints out to the console or to the file, so we don't expect anything back. And then that function will return another function that takes the level, that returns another function that takes the message. And finally, that gets printed out to the console. You see, what I'm going to do to the logger function is I'm going to transform it manually. This is a manual query, and then we're going to learn how to automate it in the next section. A function that gets transformed into a combination of 3 functions. A function that takes a resource, that returns a function that expects the level, and that returns another function that expects the message to be written, and finally returning void. Let's look at that implementation. So function curried logger takes a callable, and this is going to be the resource that we're going to use, whether it's going to be console or file, but that's going to return another callable. And this function takes the next argument in line, so it expects the level, and of course we need to bring the resource into the closure, and this also will return a callable. We're going to return another function that expects the message, also brings in the resource and the level into the closure, and returns this finally returns void because this is the function that's going to actually be doing all of the logging. And this actually is going to do the function logic. So I'm going to be invoking the resource, whether it's file or console, and I'm going to use the function string printf to print my formatted log. The first thing I want to do is print the level. The message is going to go in here, and I'm actually going to add another parameter to make this look more realistic. We'll print first the level, and then we'll add in here the date of when the log took place, just like toolkits like Monolog and others do. And for this, I'm going to use month, day, year, and also print out the hours, the minutes, and the seconds. And then finally, we want the message argument to come in. So this is basically our curried logger. What we did was take the original logger and transform it into a function that just repeatedly returns singular functions back. It's a lazy evaluated function, obviously. In the next section, we're going to look at functions that can take the regular logger and do this behind the scenes using a magic autocurring function. Using this function now is very straightforward. I can evaluate it all at once and pass, let's say that we want to create a console logger, and then the next, you can see how I'm just evaluating it stepwise. The next argument is the level, and then finally the message. This is a debug message, but that's usually how you're not supposed to use it. What we want to do is create a family of functions. So let's go ahead and instantiate our console logger. And our console logger is nothing more than evaluating this function with, actually let's create a console debugger. It's a curried logger with a console log and debug parameters fixed. So again, we'll go back to that dependency injection. I'm injecting the resource, I'm injecting the level, and what I get back is another function that I can use further. So I can create a console logger, or I can also create a file debugger that takes the curried logger and uses the file log and uses the debug level. See, I can do either one. So let's put this to the test. I'm going to take my console log debugger, and now I can use it to debug any message that I want. First log message, second log message, etc. See, now I have that function canned in there and ready to go. And this function can be passed around so that anybody can just log, to the console at a debug level. Let's try this out, and you can see that it worked. But of course, it doesn't have to stop there. I can keep going. Let's use a console warning. That is nothing more than taking our curried logger and using the console log, or in this case, let's use the file log function at the warning level. That's the level that we want to apply to the log. And then here we can do an array map. We can map this console warning function over an array that says functional PHP warning because it's way too awesome. All right, let's see how that runs. And we should expect that we log each and every one of those strings into the file with a timestamp using our curried warning logger. Let's go ahead and check that. And you can see that it did exactly that. All right, that is all for this section, and I hope you got to enjoy how you can create fluent APIs using currying. In this section, we learned that functional languages use lazy evaluation by default. Now we know that PHP is not a functional language, but we can use it to simulate lazy behavior through generators and generally through higher order functions. Higher order functions is what allows us to do currying and partial function application to create new functions with a smaller subset of the arguments. Currying is a form of partial, which transforms a multi-argument function into a sequence of stepwise inner functions, singular functions, that can be evaluated in steps. So you can actually begin to build a function in steps and pass that to other functions that can add more and make that function more specific as you go. It's always important to switch parameters or to reorder parameters to facilitate currying. And this is extremely important when you're writing functional code because all your code is going to be used through composition. And so you want to make your functions, you want to optimize your functions for currying, and you want to optimize them for composition. The goal is to take all of this learning and all of these techniques to jump into our last section of this volume, composition. And so now this is the last ingredient you need to begin to writing functional code. Hello, I'm glad you can join us for the last section where we look at function composition. In this section, we're going to learn that programs are nothing more but the sum of its parts, the sum of the composing functions. Composition is actually what glues together your functional programs, or the orchestration of your functions. We're also going to be introducing the plambda functional library, which is based on the lambda.js JavaScript library for functional programs, but ported to PHP. And this library features some very powerful artifacts known as autocurring and composition. And all of this is going to come together to create small, simple functions with dump pipes. So the idea is that we create and we dump all of our business logic into simple, easy to reuse functions that just connect together loosely via composition. Our first video is titled The Composer of Functions. As you all probably know by now, Composer is a tool that you can use to manage your dependencies. And so you can manage either your internal dependencies or external dependencies, but they're meant to be reusable. So we can say that your application code, together with all of the code spread out in these libraries, together adding up everything makes up your entire system. To put it in the words of John Gall, he states that a complex system that works is invariably found to have evolved from a simple system that worked. And what he's referring to here is what we're trying to do with Composer. What we're trying to do is put smaller systems together that are unit tested, that are known to work, to solve the bigger whole, to solve a much more complex system. And that's precisely what we do with function composition. We can orchestrate or put together a sequence of functions. Now, I haven't really shown you what all these functions mean. We're going to take a look at that a little bit later. But what I'm trying to express here is that composition is what brings together, is what glues together all of the functions that encapsulate your business logic. And so composition is that orchestration layer. It's that composer of functions. In the next video, we're going to look at defining composition much more rigorously from the point of view of programming, and also jump into some code. In this video, we're going to look at understanding composition from a functional programming point of view. In understanding the definition of composition, there are two key qualities that we need to understand, and those are of type and arity. Functions that will compose must be equivalent in type. This means that the return value of one function that will compose, the return value of one function should be compatible with the input of the next function in the sequence. And this also has to do with arity. In other words, the number of arguments that the receiving function takes always needs to be 1, because we can only return one value from a function. So this is where currying makes sense, because we can always use currying to convert a multi-argument function into a function of a single argument that's evaluated stepwise. In this video, we're also going to learn how to understand this arrow notation of the composition of two functions. Let's say that a function from B to C composed with a function from A to B generates another function from A to C. And what does this mean? Let's look at the following diagram to understand this arrow notation. And this arrow notation really comes from category theory or set theory. But in very simple terms, imagine that we have the composition of two functions f and g, f on the left and g on the right. Function f is a function from two arbitrary types, b and c. Now the function can also go from b to b. In other words, these types are arbitrary. It could be the same type, in which is called a homomorphism. But typically it's a function that goes from two different types. You can have a function like count that goes from an array to an int. On the right, we have a function g that goes from a to b. And again, two arbitrary types, but b is the exact same type as the one defined in function f and the input of function f. So the generating composition is another arrow that starts from the input of g and ends in the output of c. So it's a function from a to c. The composition is defined by the boundaries of the two composed functions. So what happens here is that the function on the right, g, that takes a and returns b, evaluates first, and its result, which is of type b, gets passed into the input of f, which then evaluates, and it ends up returning a value of c. So the initial boundary for the composition is a, and the output of the return value of that composition is of type c. Really, the best way to understand this is by looking at code. So imagine that I'm going to create a helper function called compose. Again, later on we'll see that the plambda library already defines compose, but for now I just want to give you the details of what's happening in a very simple composition. And so this is a function called compose that takes two callables. So we're only supporting here the composition of two functions. With plambda you can compose n number of functions. But the important thing to know is that composition is a function that takes other functions and returns another function. Okay, so in this way it's also called a combinatorial function. It has no logic of its own, all it does is orchestrate function calls. But this function composition, as soon as it takes the two functions, it defines a function that takes some kind of string, some kind of input. It doesn't have to be string. We're just keeping it simple in this case. But what it does is that it starts by evaluating the function on the right, g, against that input. And then the result of that function is then evaluated and becomes the input to f. And whatever f returns, that is that type of c, that's the type that ends up being returned here in this function. Okay, so the composition of two functions is nothing more than what we say is the composition of f and g is also known as f after g. Okay, so in other words, after g runs, we compute f in that sequence. So in this example, I'm showing a simple here doc with some text that what we want to do is be able to count the words. So we're going to need to basically tokenize this string, and then the resulting array, we can go ahead and count it, and that's how we can count all the words. And I can use explode, PHP's explode, to do that. But explode is a function natively in PHP that it's not curried. Again, I need to be able to be single input so that I can compose them together. So I decided to create a function xexplode that takes our delimiter. And remember, when we curry functions, we curry the dynamic arguments last, and what's most likely to change, or the data that's most likely to flow through the composition, is the text itself and not the delimiter. So I decided to curry this function, and you can see that we're returning another function that expects the second parameter, which is a string that passes through, and then finally we call explode on that. I can go ahead and partially evaluate that first parameter, which is a delimiter, and I'm telling it that we're going to break on the space. And so this gives me a little space tokenizer function. And now with a space tokenizer function, I can go ahead and do the composition of the tokenizer. Tokenizer is a function that takes a string and returns an array, and that's going to be fed into count, a function that takes an array and returns an int. And so the composition of that is a function called countWords that takes a string and returns an int. In other words, the number of words in the text. So let's see how this runs. And you can see we get 44, which is the number of words in the text. Here's another variation of this example that I wanted to show you, just for the sake of showing an example. We have the same piece of text, but now I decided to implement my own count, and I called it xCount. And xCount is a recursive function that basically chops off or works on the items of an array. And as soon as we chop off the tail end of the array, we add 1 to the count. And as soon as it's empty, we add 0 and we're out. This is the base case and it ran. And what I wanted to show you here is how recursion really makes everything functional. I'm using and passing around functions, and I'm not stopping to break the flow of the functional code to do a loop, and I'm not pausing to store any state in the loop to get, to keep the current count or to increment a counter variable, right? Everything is really done using functions. And so what happens here is that the tokenizer runs and it parses that string and it generates an array. The array is passed into xCount. xCount receives these items, and then it goes ahead and keeps count, and it keeps invoking functions. So the composition is almost nested in this case, where we're in a loop of just calling the function onto itself. And it's calling the function onto itself, but it's computing the result, diminishing the size of the input as it does that, until it reaches nothing and it returns 0, and finally that's the output of countWords, which is a string. Sorry, it's an int. So this is the exact same program. It's just now I'm incorporating recursion into my flow, and you can see that it's all just a matter of calling functions onto each other. So let's see the output of that just to make sure that it works. And as you can see, both outputs return the same exact value. In the next video, we're going to step this up a notch, and we're going to be introducing the plambda library. Now, plambda has composition functions in itself, much more powerful than what you just saw, because it's a composition function that can compose n number of functions, so we can create very complex flows made up of very simple functions. Hello, in this video I will introduce you to a library that will come really handy when you're writing functional code called plambda. Plambda is a functional library based on JavaScript's Ronda.js, and it includes combinatorial functions such as compose and pipe and curry, as well as an arsenal of utility operators that are going to help you do very mundane tasks such as counting, sorting, splitting, and dealing with arrays in various ways. The most important quality of plambda that compares it and sets it apart from any other functional library is that it's optimized for currying. This involves two things. One is reordering the function arguments to take advantage of currying. We talked about that in previous videos, so that we can make the dynamic arguments last, and most likely the one flowing through the composition chain. And the other one is that it's lazy evaluated, so it uses heavily iterators and generators behind the scenes to get the lazy evaluation happening when that's used for currying. Including pRamda in your project is very simple. If you already have Composer installed, it's just a matter of requiring this dependency. We're using DevMaster just to keep on track with the latest updates. I'll introduce you to this library following the same example that we started in previous videos about tokenizing a piece of text and counting all the words inside of it. And so notice that I'm using the curry2 function to curry a function of 2 arguments. So instead of manually implementing currying or partial or any of those, I can use pRamda's arsenal of combinatorial operators to do this. And so in this case, I'm currying the explode function with the delimiter of a space. So in other words, I'm tokenizing based on the space. And once I create my explode function, now it's just a matter of using composition. I take explode, and the output of that is fed into the count function, PHP's own count function, and the composition returns a new function. I call that new function with the piece of text that I need, and the words are being counted. So notice that I used in previous examples, the difference is that I'm using now pRamda's curry2 function to do the currying for us behind the scenes. So it's going to go ahead and augment the behavior of explode to take advantage of currying. And if we run this function, you can see that we get the exact same result as before. So you saw a simple example of using pRamda, but to better understand it, let's compare pRamda's map with PHP's array map and see where both agree or differ. So array map is eagerly evaluated just as any other function in PHP, versus pmap is lazily evaluated following Ramda's functional paradigm. Array map uses plain arrays, so in other words, you can only really use it for arrays. Anything else, if there's an object that exposes an iterator, you're out of luck there. But pmap can go ahead and take advantage of iterators. So if you have any object that implements iterators, you can actually use it. You can actually use pmap to map over functions over that object. Array map is non-curried, and this follows the whole eagerly evaluated situation. Pmap is curried, and so if you evaluate it with one parameter, it would just be dormant and return back a function, a mapping function. If you evaluate it with the second parameter, which becomes the array, then it finally executes. And because of this, array map is also awkward for composition with other functions like array filter and array reduce. It kind of gets really verbose, and the order of parameters becomes really tricky when you're dealing with combining these functions, and we're going to see a little bit of that later. But pmap composes nicely with filter and reduce. It uses the exact same interface. It exposes the array parameter as the terminal argument so that you can easily compose them. Let's go back into the code and see the example of using array map versus pmap. So in this case, I'm using array map and array reduce together. And you can see from this syntax that it's starting to look a little weird. And imagine if we were to extend this to a lot more functions that are composing. Now this is the more succinct way of writing this, although not the clearest one. And there are a few things happening here. So for once, we can recognize that this is a simple adder function. We can definitely split that out into a separate adder function and include that in there. And the other thing to point out is that the power function in PHP, the native power function, is really not optimized for currying, because the dynamic argument, which is the number to raise the power to, is the first argument, and then the next one is the base. So certainly those can be flipped to take advantage of currying, since you're more likely to raise many numbers as you map over a collection to raise numbers to a certain power, and not the other way around. So we're going to do that. We're going to take this power function and create our own that inverts this order to be optimized for currying. So let's see what that looks like. Using pRamda, I'm going to create a version of power called xpower. The original power function takes two numbers, the first one being the dynamic parameter and the second one being the base. And in this case, what I'm going to do is flip that order. Just simply flip it. Put the base argument first and then the dynamic argument last. Again, I can't emphasize that enough. We talked about this early. When we're optimizing for currying, put the dynamic argument last, the number that's likely to be flowing through the composition. The only thing that this will do is just return the power function, the output of the power function. So we have xpower at our disposition, and we recognize that that function can be just a simple adder, and pRamda has a padd that we can plug in to do exactly that. So functional addition is really done for a collection of elements by reducing using the add function. Starting with 0, you begin to add using the adder function, and you reduce the collection into a single number, and that's the addition of everything. But the first thing that we're going to do over that collection is map our xpower function with base 2. This just means that basically we're going to square all the numbers. Once we square all the numbers and we add them up all together, the composition returns a function that we can use to compute this sum. So let's go ahead and run this example, and you'll see that we're going to get the same output. And there it is. So now you saw a couple of examples of using plambda. Now these are very simple examples. There's a lot more that we can do, and we're just scratching the surface. In the next video, we're going to use the notion of auto-occurring to another level. We're going to raise it up a notch and solve real-world problems. Hello and welcome back to Functional PHP 7. In this video, we're going to take auto-occurring and composition and mix them together to solve real-world problems. In this video, we're going to continue the theme of taking advantage of plambda's automatically curried functions, in the sense that all or basically most of lambda's functions are lazily evaluated and curried. Because we're going to tackle a real-world problem, we're going to learn how to put our helper functions into static class methods so that we can take advantage of proper namespacing, and then we'll create deferred functions for ease of composition. The program that we're going to write computes the most decorated Nobel Prize category, whether it's physics, chemistry, or literature. And to do that, we're going to read a price.json file that contains JSON entries for each of the Nobel Prize winners since the beginning, all the way until 2016. So the first thing that we're going to do is read the contents of that path into a string. We're going to do some basic error handling, and then we're going to proceed to decode that string into JSON. So here we have JSON data. We iterate over all the prices, and then for each prize we extract that category. If the category already exists, we increment it. Otherwise, we initialize it with the count of 0. So we're going to keep track of how many categories we see, and then we're going to sort all the categories by value, and then pick the one at the top. So we're going to slice the one at the top, and that's going to be the most decorated category. So let's go ahead and run the imperative version first. And it seems like physics won with a total of 110 Nobel Prize. So let's look at the functional version now. And the first thing that we're going to look at, following that same statement that John Gall made, that complex programs evolve from very simple programs. So what I'm going to do is split out my business logic, split out all of this monolithic function into a sequence of much smaller functions, each having a single purpose. We know that we're going to be reading from a file, and we're going to do file get content. So I'm going to group that business logic under a function called read file. We know that we need to accumulate as the categories come up. So we're going to write an accumulate function that performs a reduce on the set of categories. And that reduce says, well, it basically encapsulates the same logic, right? If a category doesn't exist, create it. Otherwise, use run the increment function to increment the value in that category. So we're going to do a reduction to reduce an array and return back a smaller array. We know that we need to slice that first element. So we're going to create a first element function that basically uses the head lambda function to take the first element of the array. And we also know that we're going to need to convert from a string file to JSON. So we'll have a function called toJSON that encapsulates the JSON decode logic. Notice though that every function is lazily evaluated. And we do that so we can create this composition chain very easily. Okay, so now that we have our functional helpers and we've loaded up lambda, let's see how we can implement most decorated category. So this function is going to result from the composition of many smaller functions. So we know that we're going to be using pcompose. And composition is something that, rocking your head around it, means that you're going to have to write your functions basically in reverse. In other words, the last function that runs, the last function that you declare in your composition is the first function that runs. Remember that mathematical F after G model, right? It's the exact same situation here. So the first thing we do is read the file. And for that, we're going to be using the read file function from our app. That's the first thing we're going to do. So provided that we read the file, the next thing we need to do to that file is convert it to JSON. And we've also written toJSON function. Now we have a JSON object to work with. That JSON object declares the prices objects. So we're going to have to extract that prices object because that's what we're going to iterate over to compute and accumulate all of the prices. So let's use lambda's prop function to read the prices property attribute from that JSON. Then the next thing we're going to do, now we have a set of price JSON files. We're going to go ahead and map over that because everything in plambda is an iterator. So we can easily map over that. And for each individual Nobel Prize winner, we're going to extract the category. So now we're looping through each of the categories. Now that we've seen a category, we have to go ahead and accumulate each category with its value. So for that, we've written the app function called accumulate. That's going to generate a much smaller array from the original category array that contains the category like physics, literature, chemistry, and the count next to it. Now we have just a random set of categories, so we need to do the sorting. And what we're going to do is the default sorting in p-lambda is ascending, and we're going to go ahead and negate that so that it sorts descending. Okay? Now once we have a descending list of categories, all we need to do for that array is extract the first element. And that function, which you can read basically in reverse, and the other alternative you have is to use pipe. And when you use pipe, you would revert the order in which you wrote these to be a more natural flow, sort of like a Unix pipe program. But typically we'll use composition, and you read it in reverse. So the first thing we do is we read the file, we convert it to JSON, we extract the prices property. For each of those no-bill price categories, we extract the category object. We accumulate it, so we keep counts of each the occurrence of each category. Then we sort it in descending mode, and then we extract that first element. So let's see if we can run the functional version, and we should be able to get the same exact output as the imperative one. And that's exactly what we would expect it. I hope you enjoyed that quick exercise. In this section, we've defined what composition means. I've introduced you to the p-lambda functional library that handles a lot of the boilerplate code that we need to write into very simple yet powerful arsenal of operators that are all curried to your advantage so you can compose them better. We compared PHP's array map with a curried map so that you can see the advantages and just the simple benefits of just basically switching the order of the parameters and doing lazy evaluation, how much power you can gain in your code when you do that. And so to solve a real-world program, we've leveraged automatic currying present in the library and lazy evaluation to solve a program by composing multiple smaller programs together. Now join me in the final section for a brief course summary. I hope that I've been able to make it easy for you to make the mental leap and going from imperative into functional code. Here's a brief overview of the entire course. We started with writing more correct code with PHP 7 strict typing. This is going to give you code correctness at the compiler level. PHP's internal closure mechanism allows us to implement higher order functions. Higher order functions is basically the technological feature that makes all of this possible. We compared functional programming to other software paradigms, and you got to learn what each of the paradigms remove and how functional programming removes mutability and side effects. We studied the notion of pure referentially transparent functions. Pure functions is the backbone for the functional programming paradigm. We discussed the benefits of using recursion over loops, and you can see how recursion is the more natural approach to doing things like iteration when it comes to functional languages, but then it's also the best solution for doing self-similar problems like iterating trees or XML. Recursive calls in tail form can be optimized using a trampoline, and so we can gain the same exact performance that we get in a loop. We can use a trampoline to take a recursive function and match the performance of the loop. Basically transform that or flatten that recursive structure out into a straight sequence of functions where the function stack is not being used. We highlighted the benefits of using lazily versus eagerly evaluated functions, and you can see the power not just in performance but also readability and reusability that lazy evaluation gives you. We learned about partial application and currying, and how we can use auto-currying in libraries such as p-lambda to make composition just very easy and natural. All of these concepts together are necessary to understand and use function composition, which is the glue that holds your entire programs together. Finally, I just wanted to leave you with this program once more, as it really embodies everything that we've learned so far, starting from using PHP 7's strict typing to higher order functions, and everything that we've learned until the end. You can see that using composition, our function is completely lazy loaded in the sense that nothing is happening until I actually run the execute button here. All of my functions are leveraging higher order functions behind the scenes to give me the chance to do these function variables that are added into the composition as point free, which means that none of the arguments are really being passed to these functions. The flow of how the data is flowing through each function is not really present here because it's declarative. It describes the what of what we're trying to do, not the how. So this is point-free design, and this is also declarative design. So you can read off sort of the steps that are happening here using composition, and it kind of happens in reverse order. You can see that first we're reading a file, converting it to JSON, extracting the prices property, mapping a function to extract the categories. We accumulate all these categories, we sort them, and then we extract the first element. You can read off of this simple code exactly what the steps are to solve this problem. All of these functions are pure, all of these functions are referentially transparent, and that's kind of the prereq for all of this working. And then finally, all of these functions are also curried, so that that dynamic argument towards at the end of the function's signature is the one that's accepting the flow of the information and returning back and feeding that into the next function in the composition. I hope you enjoyed writing functional code as much as I did. And if you want to explore each of these topics more in depth, I invite you to check out this free book that is being developed in parallel to this course called Functional PHP, hosted at leanpub.com. If you wanted to port your functional programming principles in PHP from the server side to the client, I also invite you to check out Functional Programming in JavaScript from Manning Publishing, which you can get now for 39% off by using this discount code. And if you have any questions, comments, or feedback, please don't hesitate to hit me up on Twitter.